All right. Now, last class, what we started off with was simple oscillation, right? And with oscillation, I was trying to give you a bit of a physical intuition of what it really is. We talked about two examples. One was where we talked about, well, the mass and spring example, where the oscillation is with respect to this mass moving up and down, where the displacement is from the equilibrium position, right? And this displacement we can actually measure with respect to time and formulate a graph. So as it moves up, it moves, let's say, upwards is positive direction, downwards is the negative direction. So as it moves up, we can plot it as a positive movement. And as it moves down, I can mark this as a negative movement. And you will see how we get this curve or sine curve or trigonometric function over here. But point is, as this box or mass moves up and down, the displacement of it with respect to the equilibrium, positive or negative, can be measured against time, right? And that graph that we receive is somewhat like a trigonometric typical sine and cosine graph, right? And I'm going to show that to you. And today is the day we show or demonstrate the proof. So basically, you know the basic definitions over here. We talked about displacement, phase difference, time period, frequency, angular frequency, amplitude, all that is good. And the main formula you guys need to understand, first of all, is this formula. And I told you guys or explained the physical meaning of this, which is how acceleration is proportional to displacement. So if my bob over here, right, moves 2 meters away from the equilibrium position, let's say upwards. So let's say a positive displacement from equilibrium. So the string or a spring is stretched in. In that case, the acceleration downwards would be proportional to this 2 meters. Let's say that value is 4 meters per second square. That is downwards. So acceleration for me is always proportional to the displacement cos and in the negative direction of the displacement or in the opposite direction of the displacement, right? Similar to over here. So if I push it 2 meters up and my proportionality is with respect to, let's say, twice, then the acceleration will be 4 meters per second square downwards. And what is that constant that we say when we remove the proportionality sign? That constant is nothing but omega square negative, right? And negative is already here from the proportionality, but what we introduce is omega square. Now this omega square, the proof that it is indeed omega square is going to be shown down below when we do the derivation. So basically, this constant actually varies with different objects that you have. That means whatever spring you have, well, the omega square is going to vary quite a bit. So omega square, what is omega square? The angular frequency, or basically how many times, or basically the rate of change of the theta of the object, the oscillator. So basically how much it is moving up and down with respect to time. And you will see where the theta comes in when we show the graph. So just keep in mind that angular frequency is the rate of change of theta, right? How fast the theta changes with respect to time. And that squared is the constant over here. And where that theta comes from over here, because you would be imagining where we are just thinking of displacement over here with respect to time. Where's the theta coming in? We'll show that, no ways. So keep this formula in mind and it's going to make more sense. Basically, acceleration is proportional to displacement, but in the opposite direction. And when you remove the proportionality sign, you get omega square as the constant, right? And this omega square value depends on the spring you're using, type of the spring you're using. So different springs, different omega square value, different constant. Fair enough. So new topic today. We're going to talk about how we derive this in simple harmonic motion. That is this. Now, my question to you guys is, let's say I have a similar oscillating system, but the acceleration is not proportional to the displacement, or negative and proportional to displacement. Let's say it is not the case. Let's say acceleration does not increase in proportion with the displacement. Let's say that's not the case. In that case, is it a simple harmonic motion? No. Let's say when my displacement is 2 meters from equilibrium, right? 2 meters, and my acceleration, let's say, well, it's 4 meter per second square. But when I increase this to 4 meters, so I move it up again by 2 meters, let's say my acceleration comes out to be 5 meters per second square. Will you classify this as simple harmonic motion? While my displacement increased twice, my
No.
acceleration, exactly. My acceleration did not increase twice. It did not increase x2. So this means that it is not a simple harmonic motion. Although this is an oscillation, I cannot classify this as simple harmonic motion. So the identifier of a simple harmonic motion and the distinction between typical oscillation and simple harmonic motion oscillation is this proportionality or equation is always true. Keeping that in mind, let's prove that. And you will have a bunch of simple harmonic motion phenomena around you, right? And the first thing I'll show to you guys is this neat example. If I so notice what's happening. If you my target right now is to show you the blue bob moving, and the blue bob, the way it's moving, denotes how, let's say, a pendulum moves left and right. So the pendulum goes, if I try to give a qualitative description to you guys, when I have a pendulum, right? By the way, pendulum demonstrates simple harmonic motion, and I've mentioned that last class. Over here, the pendulum will have maximum velocity. Over here, when it goes to the extremas on either end, right? It goes to the extreme amplitude, extreme displacement on either side, on the positive side. So let's say this is negative side and this is positive side. In this case, that maximum point on the positive side or the right-hand side, momentarily the pendulum pauses, right? If you have seen your pendulum at home, the clock, momentarily when it reaches the highest point, it stops instantaneously. Again, when it comes back to this position, this maximum on the negative side or the left-hand side, when it comes to this maximum displacement, it again momentarily stops, instantaneously stops. Why? I can give you a very simple answer to that. If I consider conservation of energy, nothing else, just conservation of energy, at this height, notice, there is a higher potential energy or gravitational potential energy over here, right? And when it drops down to this position, what happens to that potential energy? That potential energy turns into kinetic energy. So there's a transfer of energy over here. At this state, that, by the way, total energy doesn't change of the pendulum, right? Total energy doesn't change of the pendulum. But at this height, when it goes to the extreme left, at this height, it gains certain potential energy. Not much. We're just starting off with the deriving simple harmonic motion. I just gave a recap of last class, and now I'm going to the simple harmonic motion. So what I'm trying to show over here is, notice this blue bob moving left and right. So what I'm saying is this blue bob moving left and right almost is an example of the pendulum moving left and right, or swinging, that swinging action of a pendulum. That is what I'm trying to demonstrate with the blue bob, right? So, and with that, I also mentioned that on the extreme ends, in this side and this side of a typical pendulum, on the extreme left and on the extreme right, notice it momentarily stops. If you look at your pendulum, it goes to the extreme left, pauses, drops down. It goes to the extreme right, pauses, drops down. We see that, right? And why does that happen? Notice, does total energy of a system ever change? You learned in thermodynamics, you learned in AS, you learned in IGCSE. No. In this total system of a pendulum, energy won't change. It will only convert from one form to another. Granted, no resistance is here or no heat energy is being released. So notice one thing. When this bob from this equilibrium position, EQ, equilibrium position, swings to the left and reaches this height, this new height, while going to the maxima, doesn't it gain potential energy? Yes, it does. Anytime there's an increase in height, right? Anytime there's an increase in height, there's a gain in potential energy, mgh, right? Mass times gravity times the height. This is the height. So it gains a potential energy, my friend. Great. That's perfect. Now, does it have kinetic energy at this extreme point? Nope. Why? I just mentioned to you guys that at this extreme point, momentarily, it pauses. It has a zero velocity, 0 meters per second at this extreme point, both this and over here, because it's changing its movement direction. It was moving leftwards, but now the direction of movement for the bob is going to be rightwards. So during this change in direction, momentarily, the bob stops at the extreme positions. Same happens over here. Momentarily at the extreme on the right-hand side, right? The amplitude position or the maximum displacement that we say, 0 meters per second, right? So what happened over here? Basically, whatever kinetic energy this bob had when swinging while reaching the maxima over here, it converted its kinetic energy into potential energy, right? So this is something that's happening. There's a conversion of energy throughout the process. When do you think is the maximum kinetic energy in this entire process? I classify this as 1, I classify this as 2, I classify this as 3. Let me know. Where is the kinetic energy highest?
The middle, number 2.
The middle. Exactly. Why? Because all the potential energy over here, not all, basically, whatever the gain in potential energy del H is over here, transfers into kinetic energy. And we know at this maxima, the kinetic energy is 0. Why velocity is 0 at this maxima? So when it reaches the lowest position, which is the equilibrium position, right? As the string is swinging at the equilibrium position, lowest height of all the other position. So all the P has now converted, not all the P, basically the change in P, whatever happened over here, that change transferred into kinetic energy. So maximum kinetic energy at the middle position because maximum velocity over here, right? At this position, 0 meter per second, over here is 0 meter per second. So that's what's happening over here. That is what we are modeling using this blue bob. Okay. Now, what I want to show you guys is something interesting. Okay. Just first look at the GIF over here, the video that's playing right now. You notice how the bob is moving around and how we have modeled that with a circle, with a bob in a circular track, right? The bob in a circular track, the shadow of the bob in a circular track is the blue bob. Try and understand that very carefully. So basically, what happens is if I shine some light over here, whoosh, whoosh, whoosh. So there's light source over here, and it is creating a shadow of this bob, right? Sorry, of this red ball over here onto this wall, right? That's how I'm going to explain. Yeah, any question? Okay, so basically how I'm explaining this to you guys is there's this ball over here, which is going in circles, and I've added a light source on this side, and I am seeing how the shadow of the ball, this blue one, moves with respect to time or with respect to theta. Now see how the theta comes into conversation. A lot of the people, when I explain 17.1, 17.2, gets confused. Where is angular frequency coming from? There is a conversation about displacement. Sure, we're talking about displacement x. We're talking about velocity, we're talking about acceleration. Where is theta coming from? If you pay attention to this derivation, you will understand where the theta is coming from. Okay, so now look, basically, let's model this position. If you're with me, let's model this position as 0 degree. Can we do that? We can. This is the starting point, let's say 0 degree. And what is, if this is the position of the pendulum, my friend, if this is a track of the pendulum, isn't this the equilibrium position? Notice over here, isn't this the equilibrium position? Similarly, the middle position is the equilibrium position. And the equilibrium position I'm classifying as 0 degree. Okay, I'm classifying this as 0 degree. So when my bob moves, well, rightwards over here, my bad, rightwards over here. Notice how the shadow changes of the bob from this middle ground to this red one moving a bit right, and now it creates a shadow over here, right? Hopefully I could explain what the red bob is and what the blue bob is. That is very important for you guys to understand for now. Okay, so that is the main setup. I just explained the setup right now. Okay, that's the setup. So I have a red bob moving around and the blue ball is the shadow of it. Fair enough. Now notice one thing. One by one, I'll go. One by one. One by one. First one. At the middle one, equilibrium position of the bob, blue bob, 0 degree. What is the displacement of the blue bob? Can I say the displacement is 0? If I have it over here, if I have it over here. Basically, I'm drawing the bob. Can I say at this equilibrium position, yeah, go ahead.
Could you explain again about the red and blue ball?
What the setup is?
Yeah.
So what I have is, I have on a circular track, I'm moving a red ball around. So just as what you're seeing over here, there's a ball going around on a circular track. Is that fine? The red one. Now I have added a light on the, let's say the topmost position over here, right? Do you see the light source?
So you mean the blue color?
The blue ball is basically the shadow of the red ball going around.
Oh,
Right. So from the up position, there's a light source, and then it creates, if I stop at this position, the light comes in over here, and it creates a shadow over here. Light passes through all the sides, but over here it creates a shadow, right? Because there's a red bob over here. Right? So the blue one is marking the shadow of the red ball going on a circular track. Is that clear? Okay, perfect.
Yep. Yes.
Okay, perfect. Now, uh, coming back at the first position that I have, the red one that is going on a circular track, it's in the middle position. Where is the shadow? In the equilibrium position. What is the theta of this with respect to the red bob? 0, right? I classified this as 0 degrees. It didn't move from the equilibrium position. I can classify this as 0 degrees. Okay, I'll show you how the degrees change, but stick with me right now. So 0 degrees. And what is the displacement, my friend? 0. Did the blue bob move from the equilibrium position? If this bob went over here, then there would be a del x over here, displacement. But I'm talking about the equilibrium position, the initial position. Is there any displacement? Nope. Nope. Is there any displacement? Nope. Okay. Oops. Fair. So the first position, if I mark, there's a 0 degree of the red ball and the shadow has a 0 displacement from equilibrium, marking this as my equilibrium position. The center of the line is the equilibrium position. Now look, I have plotted a graph of displacement versus theta. And notice what I do. At the initial position over here, that is 0 degrees. So notice theta over here. At 0 degrees of the red bob, what is the displacement, my friend? 0. Over here, origin. 0 theta, 0 x, I mean 0 distance covered, right? Now, if I move on to the next one, you will probably get a clearer idea. I have moved this red bob from this to this. So it is going anti-clockwise. The red bob is circulating anti-clockwise. Now at this position, tell me, what is the angle that the red one is making? Pi by 6. Clear? So now, as the red bob is at a position of pi by 6, it creates a shadow, let's say, of 1 centimeter over here, a small shadow over here, with a small displacement, a small displacement from the equilibrium. Okay, so as
So,
it goes,
sir,
yeah,
are you just showing this shadow for like for our understanding, or do we need to know like shadows of?
no. This is, I'm deriving the equation A is equals to minus omega square x. You don't have the derivation of this formula, but I am explaining how circular motion and oscillation is related. Conceptually, it is very important. Conceptually, it's very important. Most people will, you can work with this formula only and solve questions on physics in the physics paper. But I'm just giving you guys the derivation of it, how circular motion is related to oscillation. Do we get it?
Yes.
Okay. So basically, after this, you'll understand how to work with the formula and why the formula looks the way it is. That is it. And there is an important part while I do the derivation. The velocity formula, uh, yeah, the velocity formula and the graphs, those are important. Those are in your syllabus, and those you need to know. So I'm basically starting from point 0, which probably you don't need to know as much. Probably from the syllabus, they're starting from point 1, but I'm taking you from point 0 to 1 and then 1 to 10. Okay, so 1 to 10 is in your syllabus. Let's say I'm just explaining it to you. But this part, not as elaborately in your syllabus, but it's good to know. Okay, now look, basically, when I have this ball going around in this circular motion and it makes a theta of pi by 6, the shadow cost is, let's say, 1 centimeter away from the equilibrium. Fair? And this I have marked as this red point. Okay, pi by 6. When the theta is pi by 6, the displacement is, let's say, 1 centimeter. Fair. Now let's do something else. I move it to pi by 2 degrees. Okay, pi by 2 rad, my bad. And this is what? Map it onto the shadow. Isn't this the maximum displacement? This is your maximum displacement away from your equilibrium position. So as the dot or the red ball covers a radiance of pi by 2, it creates a shadow of maximum displacement or amplitude. What is this? The maximum displacement. So at pi by 2 radians, what do we have? The maximum displacement. Clear? Why? Look at the graph. I mean, look at the demonstration. When the bob covers a distance of pi by 2, sorry, covers a theta of pi by 2, the shadow made is of maximum displacement away from the equilibrium. Now continue doing this. Yeah.
Sir, when we say displacement, right? In this case, for in when the theta is pi by 2, is there a straight line like horizontally, or is there like the hypotenuse? of a triangle, but straight.
You're talking about basically you want to know which one is the displacement? What
Yeah,
we are calling the displacement?
yeah.
This is the displacement.
Oh,
So
alright.
on the shadow, so basically this line that you see, this is the path, this is this line. So the displacement of the pendulum, right? This blue bob, not the blue bob, the blue shadow represents the displacement of a pendulum going around. Okay?
The displacement is basically always in a horizontal line.
Yeah, I mean, yeah, sure. It is in the horizontal line, yes. So, I mean, yeah, a horizontal line over here, yes, if that's what you're asking, yep. So now, what I was saying is, as it covers initially pi by 6, it is a small displacement. As it covers pi by 2, maximum displacement, or what do we call technically? The amplitude, right? We call it the amplitude. Fair enough. Now, what happens when it increases? When it goes beyond pi by 2? Notice the shadow over here. Doesn't the shadow decrease? Doesn't displacement decrease from the amplitude? Yes, it does. And notice on this graph again, I have plotted when I have increased the theta beyond pi by 2, what happened? The displacement has decreased. Okay? From the amplitude, the displacement has now decreased.
Sir, is this
Fair.
graph of
Yeah.
shadow?
Sorry?
Is of the shadow, like
This is
displacement?
of the shadow. This displacement is of the shadow. The x-axis, sorry, y-axis, I have plotted the displacement of the shadow from the equilibrium.
Alright.
Right? Fair. Now notice again, I go to the sixth position, increase the radians again. So the theta again. What happens? The shadow becomes even smaller. Now let's see. It goes to the maximum over here. So what is this? What is this radian? Tell me, what is this radian? Anyone? Pi, exactly, 180. Pi or 180. Perfect. So now, yes, you guys should work with radians, right? So now the red bob is at pi radians away, and it has come back to its initial point. That is the equilibrium position. What happens in case of a pendulum? Notice if I start the pendulum moving around from this position, it goes, covers pi by 2, maxima, right? Maxima on the right hand side, comes back to the equilibrium position after pi radians. Now goes to the maximum on the left hand side, which is 3 pi by 2 now, comes back to the initial point, which is 2 pi. So this is how the radians is changing. Okay, so now again, I go back and show it to you. I have the seventh position. Now let's see the eighth position. What's happening with the eighth position? In the eighth position, it goes from the equilibrium, notice pi radians. This was pi and was pointing a shadow at the equilibrium position again. So this I marked as the equilibrium. This I marked as the equilibrium as well, right? So now when I push the bob or the ball over here on the circular track beyond pi radians, so this would be something along the lines of more than pi radians, what happens? The shadow created is on the negative side of the equilibrium, right? This is the positive side. This side is the positive side. This side is the negative side. So now I have a displacement on the negative side. Exactly what we have over here. So whatever displacement is over here in the positive side, same displacement on the negative side. So this would be around pi by 6, pi plus pi by 6 basically, right? So whatever pi plus pi by 6 is. 7 pi by 6 basically. Okay. 7 pi by 6. So at this position and at this position, same value of displacement, magnitude of displacement, but in opposite direction. So if you want to compare the images itself, compare this image and compare, well, yeah, compare this image. So both are simply moving in the opposite direction. And notice and compare this with the graph itself. The shadow of the ball going on a circular track is creating what? What is this graph? What trigonometric graph is this? Tell me.
Sine.
Sine curve.
Exactly. A sine curve. A sine curve. This is why waves comes into the equation. This is why waves come into the equation. This is why you can model oscillation as a wave. So what was this? The blue bob. I told you guys. This is simply a demonstration of an oscillation, typical oscillation of a bob. Of a bob. That is what it is. The shadow that the circular motion created was a display of typical simple harmonic motion or oscillation. So this blue bob moving around is the same thing as the pendulum moving left and right. And I basically modeled that movement of a pendulum as the shadow of a circular track. Nothing else, nothing more, nothing less. And as I did that, I could relate theta with the displacement. How? As the theta increases, just like in a sine curve, as the theta increased, the displacement increased. And after a point that is pi by 2 radians, and at pi by 2 radians, we have the amplitude A. So beyond the amplitude, it again decreases to a point where at pi radians, I have come back to the equilibrium position. So whenever you see displacement 0, what does that mean? This y-axis is displacement. Whenever you have displacement 0, displacement 0, displacement 0, what does that mean? The bob comes back to the same equilibrium position. Nothing else. Simple. So when I keep increasing the theta beyond pi radians, what happens? Now the displacement is in the negative axis. Notice over here. So the moment I increase the theta or the radians beyond pi radians, I have displacement in the negative axis, meaning negative displacement. Right? Right? This is how it works. And I can show it with this bulb as well. If I start off with the equilibrium position, I move it right, which is positive, let's say, taking right hand side as positive. This is my convention, positive, and this is negative. This is my convention. So how much have I moved now? To the maxima. What is the radian over here? Pi by 2. Right? I come back to the equilibrium. What is my radian right now? Pi radian. This is pi radian. Okay. So I go to the, again, starting from 0. I go to the maxima. What is my radian over here? Notice maxima, amplitude, pi by 2. I come back to the equilibrium, right? What is my radian? Notice equilibrium, pi radian. I go swing to the maxima on the negative end. What is the radian over here? This maxima, but on the negative axis, meaning negative maximum displacement. Basically, maximum displacement on the negative side. And what is this theta? 3 pi by 2. 3 pi by 2 over here. And it comes back to the equilibrium. What is this? 2 pi. So this one. That is how we have modeled this graph, trigonometric function. This is what it means, right? This is how and why we have angular frequency. Okay, this is why we have angular frequency. We say angular frequency. Well, this is why the concept of angle comes in. So hopefully I could clear why angles are related in SHM, simple harmonic motion, right? In oscillations. So we have connected. Till now, the understanding I want you guys to have is theta, or the angles, are related to displacement in simple harmonic motion. So basically, the theta is related to displacement in simple harmonic motion. That's it. Very accurate. this uniform circular motion that you have of the red bob can be modeled as a sine curve, where y is the displacement, x is the theta. Great, great. Now I'm basically creating an equation. Follow me right now. Follow me right now. I'm creating an equation right now. Okay. So what is in the y-axis? I have displacement of the shadow. Great. I have the displacement of the shadow or the pendulum on the y-axis. And I have the theta on the x-axis. That is the theta traveled by the red bob, of which we are taking the shadow of, right? So I have x as theta, I have y as displacement. Fair. So now on the y versus x graph, what is this function that you have created? And as you guys answered, this function is y is equals to sine theta. So this y in terms of x. So this is now your equation of displacement. Okay, of a of a oscillation, of an oscillation, simple harmonic motion oscillation, right? So based on the theta, you can find out the displacement of the object. How do you get the theta? Well, I'll go and explain it to you. By the way, this is x-axis, not displacement. Don't get confused. This by the x over here. This is x-axis, not displacement. X-axis. Don't get confused. Okay, x-axis. That is not x. X denotes your displacement in general, but over here when I wrote x, it means the x-axis. So the x-axis is theta and y is the displacement. So basically, displacement is equals to sine theta. You can also write this. Fair enough. Technically, you're right. So now I can say let displacement
Why
be,
is
yes,
displacement equal to sine theta?
because what is this graph that you have put out?
The sine curve.
Sine curve. So with respect to theta, how is the displacement changing? As sine theta. Okay.
Yeah.
So y displacement is equals to sine theta. If you
Oh, okay.
put in pi by 6, what do you get? You get the displacement at pi by 6. If you put in pi by 3, what do you get? The displacement at pi by 6. If you put in 7 pi by 6, you get negative whatever the value is, displacement. Right? Got it?
Yeah.
Perfect. So now this is where understand this is in your syllabus again. So now what we're modeling, what we're saying is the displacement is x. So what I have written over here, focus on that white border. I can say displacement is x. So x is equals to sine theta. On page right now, remember x means displacement. So I've basically changed this displacement as x. Fair. And sine theta is sine theta. And now I'm going to include something called amplitude. Okay. Why am I doing this? Why am I doing this? Basically, what it means is this A denotes whatever the maximum displacement can be. Okay. So let's say I have a pendulum, just to let you know that why can't it just be x is equals to sine theta? Okay. Why can it not be x is equals to sine theta only? Why do I need the A? Well, do you guys know the range of sine theta? How much can sine theta vary? What is the
Well,
maximum value of sine? Yeah, go ahead.
90, right?
No, the sine theta output. So whenever whatever theta you put in, what is the maximum sine theta output? Yeah, one. You said one.
-1.
One and minus one. Perfect. So now my question to you guys, or my statement to you guys is sine theta, sorry, my displacement can be more or less than -1, right? My displacement is always not going to be 1 or -1. It can be 1000, it can be 50, it can be 300, right? It doesn't have to be 1 or -1. It doesn't have to be 0.5, it doesn't have to be 0.3. none of the values between -1 and 1. It could be something that is, let's say, 300 or 3000. If my pendulum is really large, it could be moving like 30 centimeters away. So how does x is equals to sine theta give me the displacement? It can't. Maximum value that sine theta can give me is what? 1. The minimum value that sine theta can be is -1. So is this equation giving me the right answer? No. Nope. So what do you have over here? You have something called an amplitude, A. And how does this work? What is sine 90, my friend? What is sine 90 or sine pi by 2? Yeah, 1. Perfect. And let's say the maximum displacement of this bob over here is 30 centimeter. The amplitude of that bob is 30 centimeter. So now, if my A is 30, wouldn't this give me the right answer? X is equals to 30 now. So I have plugged in A in front of the sine theta to give me the right answer every single time of the displacement. Meaning, whenever sine, let's say, is the theta is, let's say, 90 or pi by 2, the output I get for the sine theta is 1, but my amplitude is not 1. My amplitude is what? 30. And when you decrease in theta, sorry, when you increase in theta or decrease in theta, the amplitude shifts accordingly. Not the amplitude, but the displacement shifts accordingly. So let's say, um, for the same example where the amplitude is 30 centimeter, that is the maximum displacement of the pendulum is 30 centimeter, basically. Left or right, doesn't matter. Okay, so let's say x is equals to 30 sine of, let's say, well, pi. What is my displacement going to be? What is sine pi? What is sine of pi?
0.
0. So isn't my displacement 0? Well, it is. My displacement is indeed 0. Okay. Similarly, if I take another value, well, let's say 5 pi by 6. So now, for this example, whenever my theta is 5 pi by 6, the value I get will be, well, I can just show it to you guys. Where is my calculator? Okay. Thirty times sine, oops, pi divided by 6. Nope, 5 pi by 6. 5. Okay. What value does this give you? 15. Okay. So half the value. 5 pi by 6. Typically, sine 5 pi by 6 is 0.5. Okay. Probably you guys, I don't know if you guys have memorized these values for sine outputs and cos outputs. Once upon a time I did for sitting for advanced maths or P1 or P3, I don't remember. But we had to memorize it for some reason. Basically, sine 5 pi by 6 would be 0.5. Okay. So what will be the displacement for this pendulum at sine 5 pi by 6? 15. Right? 15. So the displacement over here for 5 pi by 6 is what? 15 centimeters. Okay. Okay. Do we get the idea? Any confusion?
No.
Also.
Okay, perfect. So that is why we include that A in front of sine theta. That is the importance of it. And in general, you guys have worked with amplitude. You guys know why it's important. Give me a minute, please. Sorry. Right. Yeah. So in general, you know what amplitude is, so that you guys are not too confused. So now this is your formula for displacement of an oscillating object. If you know the theta of that object, or at what theta the object is, let's say if my object starts oscillating from this position, this is my initial position, equilibrium position. If it's at that position, what is the theta? I told you guys, pi by 2, right? Now, if it is at this position again, what do we say? We say it is at pi position. If it's at this position now, what do we say? At what position is it? 3 pi by 2. Okay, and anything in the middle is basically the whatever comes as decimal points, right? I'm just showing you the whole number once so that it's easier to understand, right? But the idea is the same. Whatever the decimal points are, doesn't really matter. It could be pi over here. Sorry, this is 0. This could be pi by 3. Say pi by, not pi by 4, pi by 6, let's say, right? And then pi by 5, let's say. And then this is pi by 4, let's say, right? You see, as the radians is increasing, it is moving more towards the right hand side. Notice over here, as the radian keeps increasing, it increases in height. Sorry, this is pi by 2. Pi by 2 is 90 degrees. My bad. Pi by 4 is 45 degrees. But yeah, you get the point. As the radians increases, your displacement increases, right? So this is how we are understanding theta with displacement. So when someone tells you my bob is at a position of 3 pi by 2, do you know where it is? Well, you should. It would be the maxima on the negative side, right? The maxima on the negative side. Fair? Fair? So basically what we're doing is we are relating the radians. Yeah, go ahead, ask.
So will the maximum displacements always be at pi over 2? Like even
Exactly.
on a pendulum?
Exactly. Whenever your displacement is expressed by sine theta, and I will show this to you, that your displacement can be expressed as cos theta function as well. In that case, it's different, and I will show you why, but don't worry. In your syllabus, they will mostly and always explain sine theta as, sorry, explain displacement as a function of sine theta. I will show you how it can be expressed as cos theta as well. The initial condition change in that case. So the bob starts at a different position. But yes, you are right, 100%. If your displacement is expressed as a sine theta or as a function of sine theta, your maximum is always at pi by 2 and minus 3 pi by 2, right? Maximum on positive end, maximum on minimum end, sorry, negative end. Got it? Fair? Is that fair?
Yes, sir.
Perfect. So now we get how the radians or the theta relates to the displacement. That much we understand. Now look at this. So one more addition to the information is the equation is not complete with theta. The equation actually includes omega t, not theta. Okay. And now it will start making more sense to you why that is the case. So when you see graph, you won't see displacement versus theta. What you will see is displacement versus time. And this is why it's useful. So you will be like, wait. I just graphed my thing in a displacement versus theta axis. How is it going to translate into a displacement versus time axis? It will. It will make sense. Let's see. So now what is the equation that we have? X is equals to a sine theta. Fair enough. What do we know of omega? So basically what we're trying to do is we're converting this equation with respect to time, not theta. And just to add a bit before I deviate a lot more, when you have oscillations taking place, you measure with respect to time. You see, okay, 10 seconds have passed, how many oscillations it made? 20 seconds have passed, how many oscillations it made? Or 100 seconds will pass, at what position will the pendulum be at? So your conversation is often with respect to time. The measurements you take are with respect to time. Okay. Which is why the theta conversation is not as useful. But we understand the displacement versus theta so that we can move on to this graph. So let's see how can we convert this x is equal to sine theta in terms of time. So we want to find displacement with respect to time. So if 100 seconds have passed, I want to know exactly where my pendulum is, where my bob is. That is why we want to convert this. So if you have looked at this, probably you understand by now. How do you express omega? Change in theta by change in time. Perfect. This is the definition of omega, angular velocity or angular frequency, whatever you want to call it. No worries. Right. So can I express theta as omega times del t? Yeah, I can. Yeah, I can. So now notice this. Let's say my omega is around 2 pi. Okay. Let's say my omega is 2 pi. 2 pi omega is 2 pi. This is I'm giving you an arbitrary value. Okay. So when 1 second has passed, how much theta will have passed? Any idea? Del theta is basically omega times del time.
By the way,
So
sir,
omega, yeah,
I want to ask here, what's the unit of angular frequency?
angular frequency. Yeah, rad per second.
It's the same as angular velocity.
Yeah, it's the same thing. It's the same thing. Everything is same. It's just we have given a different name.
Even
And last
even
class,
when
yeah,
we express it in terms of frequency, which is in hertz,
what do you express in terms of frequency?
angular frequency, like W is equals to 2 pi f, right?
Oh no, you don't really write in terms of hertz. No. Usually you don't. Yeah, I mean technically if you do the dimension analysis over here, yeah, sure. 2 pi you do write hertz, but hertz can be broken down into simpler basic units. You guys have base units, sorry. You guys have studied base units in what physical quantities. So yeah, hertz can be broken down into simpler units, right? So that is why we don't really write hertz. Although it is not technically wrong. Hertz is a derived unit. I first class probably I talked about this with you guys. Hertz is a derived unit. Now, what you're saying is not completely wrong. It is okay if you see somewhere it's written in hertz, but hertz can be broken down into seconds, right? So it ultimately it turns down into distance down into rad per second. Okay. So yeah, we do right rad per second. Now, what I was asking you guys, if I have the bob moving with an angular frequency of 2 pi, that is every second the bob travels 2 pi. What does that mean? If I have a bob over here, if I have a bob over here, it goes pi by 2, it comes back pi by 2, so pi radian in total. It goes, it's too small for please. I don't like it. Okay. So yeah, it goes right, pi by 2, comes left, total radians passed is pi, and now it goes to over here. So what is the total time over here? Sorry, total radians over here, 3 pi by 2. Now it comes back to the same position. Okay, comes back to the same position. So now total radian elapsed is 2 pi. So notice the change that has happened. In all of this
But
happened in
here,
what? One
it
second.
won't
Yeah.
always be 2 pi, right?
Sorry.
Like the total, once it comes back to the same position, the
Right.
total, it won't be 2 pi, right? It won't always be.
It will be 2 pi. When it comes back to the same place, it will always be 2 pi. That is one complete oscillation.
So the maximum but angular displacement is always pi by 2.
Yes. When you're expressing in terms of sine, yes, always pi by 2. Pi
But
by 2,
before the
and notice this 3 pi by 2 on the negative side, right?
yeah, but I
Yeah.
think before you showed when the maximum displacement was pi by 4.
No, no, it is pi by 2. But if I somewhere I did write pi by 4. I over here I wrote pi by 4. That was my mistake. Sorry.
Okay.
By mistake I wrote pi by 4. Pi by 4 is if because I was thinking in terms of degrees, then I was converting. Pi by 4 is actually 45, right?
Yeah.
Yeah, that is, no, this is not maxima. Pi by 2 is maxima. Pi by 2,
Okay.
90 degrees is maxima. This one. And also this one. This is 3 pi by 2 or 270 degrees. Let me be more specific. So 90 degrees and 270 degrees. These two are the maximas. One on the negative side, which is 270. The other is on the positive side, 90 degrees. Okay, great. So I was telling you guys, if my omega is 2 pi, what does that mean? Every 1 second, what is the radian covered? 2 pi. So it goes from equilibrium over here, pi by 2, then comes back pi by 2, total pi, and then moves to the left another pi by 2, total 3 pi by 2, and then comes back to the equilibrium again. So total is 4 pi by 2 or 2 pi. So now I ask you that for this example, for this pendulum, if 1 second has passed, what is the theta covered? Tell me.
2 pi.
Exactly. 2. Because omega is what? 2 pi times how many seconds covered? 1. So 2 pi. Now, if I tell you 0.5 seconds, what's the answer?
5.
Perfect. So the idea I'm trying to build over here is your theta changes with respect to time. This is what I'm trying to establish over here. Okay. What I'm trying to establish over here is that the idea of radian or the theta changes with respect to time. My omega doesn't change, does it now? No. If my pendulum is moving at an angular frequency of 2 pi or 3 pi or 4 pi or 0.5 pi, what does that mean? If it is 2 pi, it means it covers 2 pi radians or one oscillation every second. If it is 4 pi, what does that mean? It covers 2 oscillation every second. Very fast movement of the bob. Every second it covers 2 oscillation. So it goes to the left, goes to the right, comes back to equilibrium, right? So my angular frequency omega never changes of any object. It always remains the same. Granted, there's no air resistance and all, or any sort of friction for that matter. So granted, there is no such thing, and this is a given in this chapter, until unless you go to damping. Damping there, you consider resistance. I'll teach you guys that. No worries. So basically, the point is over here, omega doesn't change. What changes? Your time. So what do you think happens as time increases? The theta covered keeps increasing. If I go back to that initial thing, right, and I take my same example of omega is 2 pi, again, lack of space, go up. What do you think is going to happen in uh, so this is basically, yeah, let's ask this. So what do you think is going to happen over here in 1.25 seconds? What will be the angle covered? So my omega doesn't change, 2 pi, and the del t I'm telling you guys, 1.25 seconds have passed. What is the theta covered?
5 over 2 pi.
Yes. Yes. 5 over 2 pi. 5 pi over 2. Right? So what is happening over here? Now the conversation becomes you extend this graph. You extend this graph over here. By the way, the class started 1 hour before, if you want to note the time down in your local time. Okay. Uh, oh, I forgot to give you guys the class recording for this one. My bad. Give me one moment. I'll just put the link of this class here right now. You'll find the recorded version in the link provided when the uploading is done. We'll find it over here. Okay, where is it? Products. Batch. Today is Sunday. No, Monday. Okay.
Here, do you do
Yes,
classes
sir.
for separate batches?
For other batches,
Like do you do like 3 separate batches, right?
yeah, those are paid batches.
Or
Those are long-term batches, so they have been studying for a long time.
uh, no, I was thinking maybe it would be if you did like many batches together, maybe it would be easier if everyone was together, then you wouldn't have to do so many. But it's okay.
Yeah, no. So basically, they're doing the 5-month one. So 5-month ones are paid batches. Basically, we do like papers and everything. That is before that, not before start the channel, but channel wasn't doing. I wasn't doing so much on the channel. So they knew me, and then they started learning from me. They're on different pace. They're, I guess, 2 chapters ahead of you guys, 2 or 3 chapters ahead of you guys. Pretty much the same thing though. And okay. Yeah, I would actually, that would be easy if I could join the batches. Okay, did you guys get the link? So over here, I will upload this class's recorded lecture. Okay, if you guys want to save it for later reference, no worries. So if you've missed any part of this class, you can just check those first 10 minutes or 1 hour. Okay, so yeah, 5 pi by 2, correct. So basically, if I denote that on the graph, what does it look like? I extend this graph over here, right? Isn't this another maxima? Yes, I showed you guys the maxima. I asked you guys what the what the uh, degree is passed over here for the maxima, right? And you guys said 5 pi by 2, which is correct. So this is actually a continuous graph. Got it? So this is the beauty of using displacement against time. As time increases, your graph continues. Okay, this is a continuous graph over here. So now, if I tell you guys after 5 seconds for my omega is equals to 2 pi bob, can you find me the theta elapsed? Sorry, not the theta elapsed, the displacement. Can you guys find me that? Yes or no? If I tell you guys 2 seconds, after 2 seconds for this bob, can you tell me what the displacement of the bob is from equilibrium? Do you think you can? No? Well, for one thing, you can at least find the theta. Because you guys just gave me this answer that after 1.25 seconds, what is the radians passed or the what is the degree passed? And you guys said 5 pi over 2. Correct. Correct. So if I put this instead of the theta, remember over here, won't I get the displacement from equilibrium? Yes, I will. So I can just sub in this theta as omega del t. Okay. So that is what I do. Now my equation becomes x is equals to amplitude times sine omega del t. So if you know the angular frequency and I tell you when to find the displacement of, can you guys find me that? Let's check. Let's check. Let's check. Okay. Let's say the angular frequency is omega is 7 pi, a is 10 meters. By the way, always work with SI units. Oh, question will give you centimeters, whatnot, decameters, convert to SI units. And my find the displacement when time is
Sir,
330
can
seconds.
that
Yeah,
can the angular speed or frequency formula be used as W equals to theta by T instead of changing?
theta by del t. Which one? So this can be 2 pi by time period or del theta by del t.
So it can't just be theta by t.
Theta being total radians covered and t being total time covered.
No, like for example, they say they just gave an angle, and it took this amount of time to go
Yeah. Then
through
you
this.
can. Yes, that is del theta by del t. Okay, that is indeed del theta by del t. So if they're telling you, I'll show it to you. So if they give you, for example, the bob covered 3 pi by 2 rad in 10 second. Is this what you're asking? Can you write 3 pi by 2 over 10? Is this what you're asking for omega?
Yeah.
Yeah? Yes, you can do this. This is del theta over here, and this is del t over here. Okay.
Yeah.
So in how many seconds elapsed, how much theta was covered? Del theta and del t is just that. Del theta means how much radian was covered. Del t means how much time was taken to cover that radians. Got it? Yes, you can use that.
Okay.
Okay, perfect. So just give me the answer for this. Type in the chat, tell me, no worries. Oop. What is the displacement at 330 seconds? Use this formula. Start. This is important. This is what you're using
When
way
we
too
doing
much.
anything in pi, do we set our calculator to radians?
You should always have your calculator in radians. Answer should be in radians, yes. If you write your answer in exact, that is in terms of pi, even better. But if they ask you to significant figure, convert this to decimal. If they tell you exact, give me the exact answer. Keep in terms of pi. What did you say the answer is? Sorry, I couldn't hear. Someone just said the answer. No?
0.
Displacement is 0. Okay, let's find out. Fair. Let's see. Interesting. There's an easy way to say it's 0 without even doing the calculation. Can you explain how it's 0 without even doing the calculation?
If we know sine is between -1 to 1.
Okay. Yes. Oh, let's actually see by calculation what happens. So yeah, sine is between -1 and 1, but like over here, why would it be 0? Let's see. First, let's see by calculation what happens. Okay, what is the equation? Amplitude. What is amplitude? 10 meters. Times, what is my equation? Sine. What is my omega? 7 pi. Oops. What is the time elapsed? 330. There you go. There you go. And the easy thing that I was saying, why is it easy to say without even doing the calculation? Do we understand what I wrote over here? Yeah. Did anyone not understand what is over here?
I didn't
What I wrote?
understand.
You didn't understand, yeah? So look, interesting. This is very interesting. Look, wherever n is going to be an integer value or whole number, integer whole number, times pi, sign of that will always be 0. You want to check? Sine. Why do I keep doing that? Sine shift pi times 5. 0. Let's change the number. 6 pi. Why do I press calculate? Sine 6 shift pi. 0. Can I change the number? Give me any whole number. Any whole number. Doesn't matter, odd, even, doesn't matter. 33333. There's 0. What happens if I put in decimal? Okay, and now I have a value. Why is that the case? That is the nature of a sine function. Look at the sine curve. 0 degree, pi degree, 2 pi degree. When is my sine giving 0 output or 0 displacement? 0. When? Whenever it is a multiple of pi. So if it's 3 pi, what will the displacement be? 0. So 3 pi will basically be this. This will be 3 pi. If it is 4 pi, what will it be? Again 0. Any whole number multiple of pi, n pi in maths, when you're going to grow up in university, let's say do engineering, science, STEM, you'll have to create equations, you'll have to work with series, you'll have to understand how to manipulate a set of number and define that using a simple denotion like this, right? So in this case, for example, I have explained the simple thing that sine of any whole number times pi will always be 0. By saying sine n of pi, n times pi is 0, where n is a whole number. Okay, n is a whole number. Any confusion right now? Do we still not understand why this happens? Yeah. Okay, perfect. So this is why I told you guys it's easy to understand. Time over here, what is inside the sine function? Omega times t. Is my omega in terms of n pi? Yes. 7 is a whole number, and there's a pi. And what is my time? It is a whole number as well. 7 times 330. Will it give me a decimal value? No, it won't. It will give me a whole number as well. 7 times 330 will give me a whole number. So it will be a whole number times pi. Omega t will end up being n pi, where n is a whole number. So I can easily say my displacement will be 0. So this is a very interesting example that I just made up, and I didn't know this was going to be 0 until you mentioned it's 0, and then I was like, oh, right, it's supposed to be 0 because it's a whole number. So I just shared this with you guys. Okay, and it's also important maths as well. It saves you a lot of time of it. Okay. So that is the entire point. That is how you know with respect to your theta, right? You can find the displacement. That is what we found out over here. With respect to your theta, you can find the displacement. And now we did a bit of further understanding as well, where we understood, okay, I can relate theta to time as well. And now, with respect to time, I can always find out the displacement. So if I tell you, for my bob oscillating, 13 seconds have passed, can you find me the displacement of that bob at that exact 13th second? Yes, you can. Granted, I've given you the omega of that bob. You can, okay? You can find it indeed. This, note it down. I'm telling you guys, very important. This point onwards, we'll be looking at some derivations. What's the time? Okay, 60 minutes. Now, so someone was telling me, asking me, is it always pi by 2 where the maximum takes place? So is it always pi by 2 rad for maxima? Not necessarily. So let's say your oscillation starts from this position, the maxima itself. Yeah, any questions? Okay, so I'll just draw this. Okay. So let's say my bob starts oscillating from this position, position 1. It is already at a maximum, no? So I've pulled it, and now I start my t is equals to 0 at this position 1. So I start my stopwatch at t is equals to 0 to find out how many oscillations it will do in 10 seconds, let's say. Okay, that's what the experiment is for me. In 10 seconds, I want to find out how many oscillations my bob does, my pendulum does. And I start where? It is at this extreme position or that maxima. So what is the right? Yeah. Any question? Okay. So now over here, what is the starting theta at t is equals to 0? You, well, you could say that it is pi by 2 technically with respect to this diagram, but no. T, if time is 0, theta elapsed is 0. Okay. How did we find it out? How do we explain theta, my friend? Omega times del t. So sure, when you look at this diagram where the starting position is, it is at a pi by 2 radians displacement away from the equilibrium position, fair enough. But when we're doing the maths, how do we explain theta? Omega times del t. So when my del t is 0, what is my theta? 0. So this starting position, if this is your starting position, the maxima is your starting position, your theta is 0, not pi by 2. And this is no longer a sine function that you will see. This will be a cos function. Why? Because cos functions have a maxima at 0 degrees or 0 radians. Do they not? Do they not? They do. So this now is no longer x is equals to a sine omega t. This is what? This is x is equals to a cos omega t. Will you get this? They can trick you. They can trick you and say, well, I'm starting my pendulum from the maximum point or from the amplitude position. Define the displacement and you define it as this. Not as sine. Nope, nope, nope. Because theta is 0. Sine theta is 0. But at my theta is 0, over here, displacement is max. X is max. And
So we
when is
always
X? Yeah,
we always
yeah.
consider that to start from our initial point.
Sorry, could you repeat that?
So we always consider theta to start from our initial point, right?
Right, right, right. So now you have at theta 0 times 0, you have x is equals to max or x naught or amplitude. And how can you explain this as a trigonometric function? As a cos theta function. Okay, because cos produces a maxima at 0 and at pi. Okay, got it? Got it? Fair? Because look, uh, this maxima will only be produced when it needs one entire rotation. So it goes and comes back to this position, and only then a maximum will be produced, positive maxima. A minima maxima will be produced at after pi radians. So yes, over here again, notice pi. At pi radians, there's a minima, and at 0 and 2 pi, there is a maxima. Okay. So this probably is not necessarily going to be shown to you in details, but this part will be shown to you when you study again, if in your school or somewhere else. But yeah, point is, do you understand why there's a cos theta? Why we say we can explain it as x is equals to a cos omega t? This is the reason. That it depends on the initial starting condition. Depends where you start the bob from. Okay. So if start your time with the bob at the position 1, then it's a cos function of displacement. And we start the time from the bob being at the position 2, then it's a what function? Sine function. And take my word for it, you guys will be working with sine functions. Okay. Is it lagging? I hope not. Is my screen lagging, guys?
Yes.
It is.
What's into this?
Sorry, could you repeat that?
So, what were you asking, sir? What screen?
Oh, is my shared screen lagging?
Oh, no.
Okay, so I'm with another device as well. For some reason, it's not showing over here. I can continue, but I don't know why it's not showing. Wait.
Okay, sir, I wanted to ask,
Yeah,
so we know that in simple harmonic motion, right? The
yeah,
acceleration and displacement are in the opposite direction, but are directly proportional to each other, right?
perfect. Yes,
And the proportional constant is W squared. Why is it W squared? Why is W
right,
constant? Do we
right.
need
Why
to
is W squared the constant, right? Isn't that the
Yeah,
question?
yeah.
Perfect question. And this is the of this. This is step one to proving your answer. I mean, answering your question. So I'm going a bit step by step, but yes, I'm going to answer your question indeed. So it's not in your syllabus why omega square is the constant. You don't have to derive that, but I will show it to you guys. No worries. So that what you have written down right now, x is equals to a sine omega t. This is step one. Step two is finding. Oops. Oh God, wait, give me a moment. I just signed out from one this other thing. Why am I signed out? My bad, guys. Give me a moment. Okay. Perfect. It is recording, thank God. Okay, yeah. To answer the question, why it is omega square, I will prove that to you. No worries. And this is the step one. You can write in what do you say? You can write in steps as well. Step one, find the displacement. Step two, find the velocity equation. So are we clear how to find the displacement? Any question till this point? Any question? This is what you will use, the sine theta, sine omega t function. Find the displacement. One, you don't use it. Again, I'm telling you, you don't use the cost function. You only do it when the question paper gives you a trick question. I have done a lot of papers, taught a lot of papers, doesn't come frequently. I've barely ever seen it. Probably even set in a different curriculum. I don't even know. But yeah, in general, it doesn't come. Clear? You guys understand? If you've got am I lagging? Very confused. I'm very confused. Can you guys hear me?
Yes.
Okay. Questions
Yes.
at this point, right? Okay, no questions. Now, this is what a sine omega t, where is displacement a given a second. Yeah, this had you guys that you can get, let's say, they can give you and ask you what the time elapsed. So it's sort of first operation. Give you guys the time elapsed and what did you guys find? I give you guys T and you guys found out the displacement. You can do the opposite as well. Can you not? Yes, you can. Well, let's say you the values. So I will not give you the values. What will I give you? I'll tell you, find how long it takes for the bob to reach x naught or amplitude position the first time. Okay, how long it takes to reach the x naught or amplitude the first time, given the omega is 3.5 pi. Can you guys do this? Find the time. And one example is right in front of you of how to do it. Can you guys do this? Yes or no? Yeah? Then give me the answer in about 2 minutes. 1 minute. Shouldn't take that long. You have a model answer.
Answer in Slido. Sure.
Yeah, go ahead and answer in Slido.
Can we, are we meant to see the graph or?
Are you meant to see the graph? No, no, it's not relevant. Okay, someone has asked a question on Slido. I will answer that indeed, but by today or tomorrow, I'll answer it. Answer below. There's a thing open right now. You can answer there. Okay. Right over here. Mode if you can use well it is 2321508. Answer. Join in and give me your answer. Okay. Waiting, waiting. Right, it is Horace. Yeah, here. A little while. Question was
Sir, can I see the question again? Sir, could I see the question again?
yep, sorry. My internet is pretty bad. Okay. Yeah, I have one answer right now. 4/7 I have. Good, good. One more. So I didn't hear what you said last time. I didn't really hear anything. If anyone spoke, yeah.
I was just asking to see the question.
Yeah, sorry. My just thing just signed out. I'm not signed out. Disconnected. Yeah, I can see one person typing, so I'm just waiting for that. But yeah, I will just start with steps. Meanwhile, so yeah, the steps are pretty much the same. What am I asking you guys? I'm asking you guys, when the displacement is maximum, what is the time elapsed? Okay, how long it takes for the bob to reach the maxima? Okay, the first maxima, the positive maxima. Notice it is positive. Okay, when there's no sign, it means positive. Okay, yeah.
That means theta is pi by 2.
What do you the radians is pi by 2? Yes. Yes, indeed. Radians is pi by 2. Okay. Fair. So I'll start off with the answer. How does the answer look like? Okay, I have fair 1/7 of a pi. Interesting. 4/7 of a pi. 4 by 7, I guess you mean pi. Okay, so our answer. But yeah. Now let's see. Let's try together. So my displacement, what do I want my displacement to be, guys? I want my displacement to be maximum. A. Okay, I want my displacement to be maximum or A. Okay, so if I want my displacement to be the amplitude, I can simply say A is equals to A sine, what is my omega? 3.5 pi t. Okay, I want my displacement x to be x naught or maximum. Okay, and this is the typical equation that you have, A times sine omega t. Fair. So this is your omega, 3.5 pi. This is the time elapsed. Perfect. Now, if this part we are on page with, now what happens is the A and A, the amplitudes get cancelled off. What are you left with? You're left with 1 is equals to sine 3.5 pi t. Can we do one thing over here? Can I take sine inverse? Yeah, I can. Sine inverse of 1 would be, so I take a sine inverse on either side and say, I'm just showing all steps, okay? I'm just showing all steps. I would make a shortcut, but just showing the steps. Now look, when the sine inverse and sine interact, they cancel each other off. And you're left with, if I take this to the other side, sine inverse of 1 would be, sine inverse of 1 would be, if I draw a sine curve for you lot, without even using the calculator, without even using that. Inverse function means you take the y input and find the x output. Okay, when is sine 1? When is sine 1? Perfect. Pi by 2, right? Pi by 2 or 3 pi by 2? But what did I ask you guys? Or even further, you can even extend further. You can even say, well, uh, 2 pi plus pi by 2, which probably is 5 pi by 2, 5 pi by 2, or even go even further. You say, well, 7 pi by 2, sure. It could be anything. My point is, it could be anything, but I want you guys to find the first amplitude and the positive one. Okay? So the first amplitude and the positive one is found when my radian is pi by 2. Sine inverse of 1 can be pi by 2, 3 pi by 2, 5 pi by 2, can be anything. Maths wise can be anything. But you don't take 3 pi by 2. You don't take 5 pi by 2. Why? Those are not the time I'm looking for. I'm looking for the first one. So which one do you take? The first one, that is pi by 2. So sine of pi by 2 is 1. Hence, sine inverse of pi by 2 is 1. Okay. Sine of pi by 2, if you guys didn't see much in maths, sine pi by 2 is 1. So sine inverse of 1 will be pi by 2. Hopefully this is clear. Okay. It could be pi by 2. It could also be other values. Again, I'm clarifying that. Could be all other values, but I'm scrapping all those. I'm scrapping this. I'm scrapping this. Why? I want the first positive amplitude, which is this position. So, okay. My point is now I get sine inverse of 1 as pi by 2 is equals to 3.5 pi times t. Now it's easy. Now it's making t the subject, which is pi and pi gets cancelled off. T is equals to 1 by 7. Now the answer becomes 1 by 7. So yeah, you don't have pi in the equation. So the time elapsed is 1 by 7 seconds. Perfect. Do we have any question for this one?
Sure. Here, couldn't we just have done W is equals to change in theta divided by change in time?
And you don't know the change in time.
Yeah, we're trying to find that.
Yeah.
So I could just use that formula.
Yeah. Tell me what you're writing.
W is equals to change in theta divided by change in time.
Yes. And where do you want to put this?
And then we make change in time the subject. Then we just calculate.
Oh, so you just found out the theta by saying, okay, it should be pi by 2.
The
That's what you're
maximum
doing,
pi by
right?
2. Yeah.
Yeah, sure. You can do that as well. Do you get a different answer doing this?
No.
Yeah, it's the same, right? Yeah, you can do that as well. So your instinct over here, your physics intuition told you that it must be pi by 2 because I said this, right? That's how you found out, right?
Yeah.
Yeah, but now the reason it won't always work is because they may tell you find it when displacement is 3 meters. You can't do that. You don't know what the radiant covered is in that case. What you did right now is perfect. No worries. Perfecto. But when they tell you, goodness gracious, what this is. Okay, when they tell you a specific distance, like, oh, 3 meters, what do you do in that case? Scrap all of this. Your answer now is, well, my x should be 3 meters. So I equate 3 is equals to what? A sine whatever the omega is, doesn't matter. So now you have to use this equation, don't you? You can't just work with omega is equals to del theta by del time because you don't know the del theta. You don't know how long it would take to reach 3. You don't know if 3 is the maximum. You don't know that. So now you have to use this equation. Got it?
Yes.
Okay, perfect. So great. Get used to this equation and 20 minutes. Okay. Now I want to show you guys how to find the velocity. Okay. How do you derive velocity from the equation? Let's see. Do you guys know that the derivative of distance is velocity? Or derivative of distance is speed? Do you guys know that? Calculus.
Yes.
So what
Okay.
did you just say? Please could you repeat?
So I said, do you guys know that the derivative of distance is speed or velocity?
Yes.
Yes. Of distance or displacement. And let me write displacement, honestly. So derivative of displacement is velocity. Perfect. So that is exactly the idea we use over here. Don't we have an equation of displacement? Yes, we do. Yes, we do. So now to find the velocity with respect to time, so I'll tell you what I'm finding to make a clear picture in your mind. What I'm finding right now is with respect to time, let's say if I tell you after 10 seconds, what will be the velocity of my bob? Can you find that with the current equation? Nope, you cannot. But if you have an equation which is velocity with respect to time, then you can, because you just plug in the time and you find out the velocity. By the way, are we all clear that velocity changes as the bob moves? And I tried to prove this towards the beginning of today's class that at the
Yeah,
middle
because it's
position,
elevating, right?
yes, it transfers its kinetic energy to potential and potential to kinetic. So when it's at the maximum position, velocity is zero, right?
Yeah.
Over here. Perfect. So
And
if you know that, you
acceleration is
know,
constant, right?
sorry, could you repeat?
Where velocity is zero, acceleration is maximum, right?
Yes, 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 definitely. So you're talking about the maxima. Perfect. So whenever the displacement is maximum, your acceleration is maximum, but in opposite direction. And in those cases, velocity is zero. Absolutely right. In summary, if you understand those three lines that you just said, displacement maximum, acceleration is maximum, but in opposite direction, and velocity is zero. These three things, very important to understand what you just said. Correct. So, as I was saying, what was I saying? Right. So I was just saying that we are clear and on page with the idea that velocity changes as the bob moves or as the spring moves up and down. Any case, any simple harmonic motion. So as the mass moves, swings, the velocity changes. So it is a valid question for me to ask, can you find me the velocity of the bob at a given time? How do you find it? Let's see. We first need an equation with respect to time for velocity. So what do we do? Very simple. I told you guys, or started the conversation with saying, do you guys know that the displacement derivative is velocity? You guys said yes. So taken, you guys have that prior knowledge. I will, I will take a derivative of the displacement equation, and I will find velocity with respect to it. So you guys know this prior knowledge. Velocity is dx by dt. Change in distance by change in time, right? What is v? D by t. So for any point on the curve over here, any point on the curve, whatever the instantaneous change in displacement by instantaneous change in time is, gives me the gradient of the curve at that instantaneous point. And that gradient of the curve is the velocity at that instantaneous point. What is the gradient over here at this maxima or this position 3?
Zero.
Perfect. 0. Hence, my velocity is what? 0. And with our physics intuition that we established towards the beginning of our class, it is correct. It matches. So over here, the gradient at pi by 2 is what? 0. And at pi by 2, we get the maxima. And this is exactly where your velocity is 0. So gradient is 0 of the displacement curve, hence velocity is 0. Perfect. Okay. Where is it? Right. So now, can I take the derivative of the displacement equation? We can. Let's do that. So how do we take the derivative? We're taking the derivative of this entire expression with respect to time, my friend. Okay? With respect to time, and anything else is a constant. This is a constant. Sorry. This is a constant. This is a constant. And what is the variable over here, my friend? Yes, the time. So we are taking derivative with respect to time. Yeah. Okay. Now, can I say dx by dt? That is, I take a derivative on this side, dx by dt is d whatever this expression is by dt. Yeah, I'm taking a derivative on either side with respect to time. This is how maths looks. Okay. Do you need to know it? Well, technically, yes. But even if you don't, doesn't really matter. But yeah, we're taking a derivative on either side and saying, oh, well, what is the answer going to be? Dx by dt will be, I mean, if you guys remember derivative of trigonometric functions, this will be easy for you. So if I take a derivative of sine omega t, or let's say sine 3t, what is the derivative of this, guys? Can anyone tell me? Any idea? Yeah.
3 cos 3t.
3 cos 3t. Perfect.
Wait,
So,
what did you say?
so yeah, I asked, what is the derivative of this,
Oh, okay.
right? First derivative of this. So the first derivative of this will be I derive the outer side, right? Outer equation, outer expression, and then the inner expression, right? So I first derive sine function. What do I get? Cos 3t. And then I differentiate the expression inside the parenthesis. Oops. So that is 3t. And what is the derivative of 3t? Chain rule, guys. Chain rule 3. So 3 cos 3t. Perfect. Fair enough. What would happen if it was 4 sine 3t? Now tell me, what is the derivative?
12 cos 3t.
Perfect. Cos a 12 cos a 3t. So what did we do? We simply took the derivative of the sine 3t first, which is, or 4 sine 3t first, which is 4 cos 3t times derivative of whatever is inside the parenthesis, which is 3. So I get 4 times 3, 12 cos 3t. This is your prior knowledge. Simple revisit of the idea. Okay. So this is how derivatives work. Why did I show this one? Did anything happen to 4? No. What is 4? What do we technically call 4? Amplitude of this expression, of this trigonometric function. So the maximum value of this trigonometric function is 4. When sine 3t is 1, your maximum value is 1. Maximum value is 4. So 4 is the amplitude. That is math knowledge that you guys have. Okay, fair enough. So now look, I do the same thing over here, just with alphabets. Okay, just with alphabets. So over here, how do I take the derivative? First, I take the derivative of this, sine omega t. What is the derivative of that? Well, cos omega t. And then I take the derivative of the thing inside the parenthesis, which is omega t. What is the derivative of omega t? Omega, remember, is a constant. T is the variable. What is the derivative of omega t? Omega. Where is the omega? Right in front, my friend. Okay. So now you have omega a cos omega t. Okay. Perfect. So now we get this equation. Can I write dx by dt as v? Of course I can. Look, right? Dx by dt as v. Now the idea is whatever you have in front of a trig function, that is the amplitude of the trig function. What is the amplitude of this?
43.
Perfect, 43. What is the amplitude of this?
43.
Perfect, 43. Nothing changes. Whatever is in front of the trigonometric function is the amplitude of the function itself. So if I say y is equals to 43, what is the amplitude of y? Y is equals to 43 cos 3t. What is the amplitude of y? 43. If I say y is equals to 100 sine t, what is the amplitude of y? 100. Okay, 100. I mean, amplitude of the curve. But yeah, you get the idea. So if it is it a constant, which is the amplitude?
constant. The amplitude is a constant. Displacement keeps changing. Amplitude is a constant. Whatever the maximum value is the maximum value. That is amplitude, right? So now omega is a constant. Does the angular frequency change? Nope. Does the angular velocity change? Both are the same thing. But does any of those change? Nope. So it is a constant. Both of these multiplied, granted they are a constant, is going to be the amplitude. So omega times A is what? Amplitude, my friend. Okay. So we express V naught as A omega, where V naught is the maximum velocity. You see that naught over here? This means maximum in this chapter. I don't know why that is the case. I hated this because V naught, not in general, means initial value. You guys have probably used that before. I used to dislike this quite a lot. But yeah, not over here in this chapter means maximum value for some odd reason. So yes, V naught is maximum value, or X naught is the maximum displacement. V naught is the maximum velocity. So yes, when you express velocity with respect to time, you get A omega times cos omega t. So now you have a function with respect to cos. Why? Because we took a derivative, right? And now A omega is expressed as V naught. So if I ask you what is the maximum velocity of the bob, this bob swinging, what do you tell me? The maximum velocity of the bob that can be is V naught. So if I write numbers, if my bob is swinging at a rate, or not rate, angular frequency of 4.5 pi, so if I say V naught, V is equals to, let's say 10 times cos 4.5 pi t. What is the maximum velocity over here that the bob can have, or at the equilibrium position is the max velocity, right? So what is the velocity of the equilibrium position of the bob? Tell me.
10.
Perfect. 10 meters per second. Okay. So this is the amplitude or the maximum velocity that the bob can have. Great. Both are the same thing, Vmax, or whatever you want, right? Now, this also makes sense in some other way. If you guys remember from circular motion, right? Circular motion. You guys remember this equation? Yes or no? V is equals to R omega. Remember
Yes.
it? Yeah, you do. So look at this. When I'm writing V is equals to R omega, and my R is maximum, or my displacement in this chapter, when the displacement is maximum, or A, you get V naught, the maximum velocity. So when my R is max, you get the max velocity. Hence, you can say V naught is equals to X naught times omega. What is X naught? Max displacement or amplitude, right? So see how everything is linked up together? Everything is linked up together. When I started this batch off with you guys with circular motion, I told you guys, circular motion is linked with multiple things. The reason it's important is not because of the chapter itself. It's because how it integrates itself with other chapters. That is why it's important. That is why those concepts are important. Okay. So, and that is also why I started off this chapter, not started off, but this class with this, how circular motion really relates with oscillation. You saw the bob in circular motion, and you saw how it can be translated into a pendulum moving around with the shadow. And that made me understand how I can draw displacement versus theta curve. I understood how theta is integrated. And I'll tell you guys one more thing, and this is just extra information and the beauty of nature, physical nature, that whenever you see pi anywhere, whenever you see pi somewhere, you know it has something to do with circles. Remember that. It is just for fun, anyways. Whenever you see anything to do with pi, you see pi mentioned in the equation, you see pi somewhere, you know somehow circle is related to this. Somehow circle is related to this. right? And you will see pi pop up randomly in random places. Okay, so often whenever you'll find different ways to find pi, the reason it's important is because pi is such a naturally occurring number and it's irrational. It's almost fascinating. So yeah, similarly to gravitation, we have circular motion coming in to over here. And this is why A omega makes sense. We didn't just multiply two constants up. It makes sense, that's why, right? So yeah. Anyways, if you had two constants over here and you multiply, that would be the amplitude anyways. So that's a given. So any question till velocity? Now is the part where I answer your question that we start. Why omega square? Any question till now? Velocity part? Anything?
So we don't need to know how to derive this, right? We
Velocity you need to know. Velocity part you need to know.
can I take a screenshot of this?
Yes, definitely. The first part, that elaboration zigzag, no, all that you don't need. Of how circular motion and displacement is related. Nope. Just in general understanding how that function s is equals to a sine omega t. Just understand that and what it really means. Okay, just understand that, no other thing. And this one, this derivation, you may be asked to derive velocity from a given displacement formula. Okay.
Okay.
Perfect. You're done, right?
Yeah.
Okay. Now, big question. Where on earth does the omega square come from? Why? Why is that the constant? Right? Oh, by the way, what is a omega? What is v naught? Is it a variable or a constant? Tell me.
It's a constant.
Yes, amplitudes are a constant, right? So if I give you that this curve has an amplitude of 10, that means the amplitude of the max value of that y function, y is equals to 10x. Sorry, that's a bad example. Y 10x sine theta. What is the maximum y value out of this equation? 10. 10 is the only maximum value out of this equation. And when is that possible? When theta is equals to pi by 2. Okay. When theta is pi by 2, only then we have y is equals to 10. Okay. So amplitude is basically a constant. Got it? Amplitude is a constant. Great. So if you understand that, where now look, that the reason I'm saying clarifying what a constant is remember I said omega square is a constant. We remove the proportionality sign. A is proportional to minus x, and you remove this, and we get a is equals to minus omega square x. What is this? A constant. What is this? A constant. What is this? A constant. What is x is equals to a sine omega t? What is this? A constant. A is a constant. Okay. That's why I'm flag posting this repeatedly. What is the derivative of velocity? What do you get if you did take a derivative of velocity?
Acceleration.
Acceleration. Perfect. So if I take the derivative of velocity with respect to time, I get an equation of acceleration. Okay. So now let's do that. Let's do a derivative of velocity. V is equals to V naught. Actually, I have to write it in terms of A omega. A omega cos omega t. Right. Uh, so the derivative of this, same as usual. What is the derivative of cos omega t? Does anyone know?
WT sine.
Omega cos WT.
Omega cos wt. If I just say cos omega t, this y is equals to What is y prime
Sorry.
or derivative of y?
Minus omega sine
Yeah,
omega t.
perfecto. Minus omega sine omega t. Perfect. So basically, if I do step by step, what is the derivative of cos omega t? Minus sine omega t. Okay, minus sine omega t. And what is the derivative of inside the parenthesis, inside the bracket? Omega. Okay, so y prime becomes minus omega sine omega t. There you go. That's how you get it. So derivative is of the velocity equation. There you go. Of the velocity equation, the derivative is minus omega sine omega t. Exactly what you said. And where is the a omega coming from? It was just there. It's just sitting there. It's just sitting there. Okay. Nothing happened. It's just sitting there. Nothing happened. Now. Interesting part. Uh, there's omega over here. There's omega over here. Can I write it as omega squared? Yeah, of course. Who's stopping me? Minus a omega squared. So this and this. Okay. What am I left with? Minus a omega squared times sine omega t. Guys, do you guys remember this equation? Displacement is equals to a sine omega t. Yeah. We studied this today towards the beginning of class, right? X is equals to a sine omega t. Displacement is equals to a sine omega t. Can I replace a sine omega t with x? Yeah, I can. So I write a sine omega t as x. I keep minus as it is. And voila, a is equals to minus omega square x. This is the simple harmonic motion equation. That acceleration is proportional to displacement and oppositely. And the constant is omega square. I find this really fascinating and interesting, how neatly, with simple calculus, you can derive this equation. Simple calculus, nothing too complicated. Okay. Owen, did I answer your question of how the omega square comes out to be?
Yes.
Yep. Any confusion till this point? Yeah. Okay. I've shown pretty much every single derivation that you need over here for the simple harmonic motion part. Okay. Even more than you would need in case you have any interest in the subject or just want to learn for fun. Okay. And now, if you, by the way, I didn't show you guys the graph, by the way. Over here, when you draw the graph, what is this graph function? Why? Because I'm plotting velocity versus time, right? Velocity versus time. So at 0, it is the amplitude. What is amplitude? A omega. Don't forget so fast. Okay. A omega. So that is amplitude. Okay. So it is a typical cos function. You guys know cos functions in maths. So it's just that forever, pretty much. Give me a moment, please. Give me a moment. Right. So as I was saying,
Sure.
you have,
Here,
yeah.
the one that I have starred. Why is it v equals to v naught cos? Where the a and where the amplitude and w go again?
So you can just write a omega as v naught. Doesn't matter. V naught denotes maximum velocity.
But because we're considering rw.
Yeah. So when
Oh.
r is max, your velocity is max, right? And it doesn't even matter. Even if this proof, I wouldn't give it to you right now. Why v max? even if I didn't show this to you, even then, this amplitude of this graph is what? The maximum value. The amplitude is always the maximum value. So even just looking at this, if you don't know circular motion, what is a omega denoting? The amplitude of what function? Velocity function. So the amplitude of the velocity function is the maximum velocity. So I can write a omega as v naught or v max. Doesn't matter. Equal. Got it?
Yes.
So let's. I mean, if you're still confused, if I wrote x is equals to a sine omega t, or let's say I wrote c d e f g sine omega t. What is the maximum displacement over here, or amplitude of the x curve? Tell me. Where C, D, E, F, G is a constant. Tell me what the amplitude is in this case of the displacement curve or the displacement equation. X is displacement. Anyone? Tell me what the amplitude is.
C, D, E, F, G.
Perfect. C times D times E times F times G. This is the maximum displacement. Whatever the numbers are, doesn't matter. Could be anything. I'm just showing it to you guys. Whatever the constants are, whatever the numbers are, whatever is in front of the sine function as constant, if these are constants and multiply to each other, these are the product. I mean, the product of these are going to be the amplitude. And the amplitude denotes the maximum value of whatever is over here. So if we are talking about the amplitude over here, this is the max value of displacement. If we are talking about the amplitude over here, this is the max value of the velocity. That's it. Nothing else. Nothing else. Okay, so I showed you the graph. The graph is important. Okay, the graph is very, very, very important. If they ask you guys to draw V is equals to A omega cos omega t, how will you draw? This is how you will draw. You just draw one period and that's all right. You don't need to draw multiple. You can draw it like this. Okay. They'll probably tell you draw two oscillations. So you draw two entire functions. Okay, looks like a W. Anyways, so what you plot, by the way, you also plot the if possible, also plot the x-axis. So what is this? For a typical, what do you call it? Cos function, cos theta function. Okay, my bad. This is in terms of t. So whatever the time will be in that case. So if they give you the omega, you can find out the time elapsed in those cases. So for this happens at pi by 2, right? So what will that be? Let's say I give you omega is 4 pi, just for an example, just to see if you guys understand it. Omega is 4 pi. So the del theta would be found out, or the time elapsed. When is cos function 0? Tell me, guys, when is cos function 0 at what theta?
Pi
Anyone?
over 2.
Pi over 2. Okay, pi over 2. Pi over 2 by time. So you make time the subject, okay? 4 pi. I'm just writing extra steps. Pi by 2 times 1 by 4 pi. So basically 1 by 8 seconds. Okay, when this would be what? 1 by 8 seconds. You can do the conversion. We did one math similar to this. So basically, you find the time elapsed at each of these major points. Do you need to do it? Always no. When they ask you to label the axis, they'll say something like this. Label the axis of your diagram. Then you do. Then you label the maxima. Okay, that a omega is the amplitude. Minus a omega is the amplitude. Okay, and then what do? You also label these points, these critical points. Okay, and this is 0. Fair? Fair? You can label those. So that is the v function, and the acceleration function is simple. For the sine, well, look. Do you guys remember the displacement function of the pendulum? It was positive sine function, so it looked like this, right? This is the displacement curve, the green one. Why is it different? It was a sine omega t. Isn't it the positive sine function? Yes, it is. So it looks like this. Starts off with a positive value, goes to a negative value. What is the acceleration graph? Look at this. Look at this. Minus sine omega t, right? And what is the amplitude? A omega square. Got it? A omega square is the amplitude. Amplitude, amplitude. So look, it is a negative sine curve. Okay, and you can also find the time elapsed similar using a similar formula as we did, using omega is equals to theta by t. Okay, you can use this. So notice again, if I start my bob from this position, what will the acceleration be? What is x at this position? 0. What is acceleration at this position? 0. So 1, 2, position 2, what happens? X is equals to, actually let's take to the positive thing, positive side. So this is positive side, and this is negative side. Okay. So the bob goes to this position. X is going to be A. Agreed. Zoom in. X is going to be A, amplitude, and acceleration is what? Tell me, what is acceleration going to be? At the maximum position.
Maximum.
Minus
Yeah, maximum.
omega squared A.
Yes, right. Accurate. Perfect. A is minus A omega square. Right. Isn't it on opposite direction? A is positive, x is positive, acceleration is negative, and maximum. Okay, x is also maximum. So it goes back to 3. What happens? X is equals to minus A. Okay, and what is acceleration? Last question, you guys.
Omega squared A.
Perfect. Perfect. By the way, just one thing to tell you guys, in general, it doesn't matter as much. Whenever you write variables down, or your answers down in terms of, let's say, A, B, C, D, let's say in this case you have A omega, you start off with the smallest alphabet. So it starts off A, B, C, D, E, F, G, X, Y, Z, right? So what did I even say in terms of alphabets? Or whatever, the 26 alphabets. Basically, you write in chronological order. So whatever is this first, you write A first, then omega. Why? W comes later in the alphabet series. Will anyone ever cut marks for this? But if they're really, really petty and they just want to cut your marks, but I've never seen. I would never cut anyone's mark for this. It's just, I'm telling you guys, it's a convention in scientific writing. Okay. Maybe probably someone told this to you guys earlier on years as well. Now, in summary of today's class, this I've extended the class a bit, 15 minutes, sorry. So this is, you can take a screenshot. In terms of x displacement equation, x is equals to a sine omega t. What is the maximum value? A. In terms of v is equals to v naught cos omega t. What is the maximum value? V naught or a omega. Okay. In terms of acceleration, what is the maximum value? A omega square. Okay. And when do we get this? When sine omega t is -1, because there's a minus sign over here. Okay. So when x is equals to minus a, you get this maximum acceleration. Any question till this point?
No.
So what about when x is equals to a?
Then your acceleration is minima. X is equals to x is equals to a. Hence, your acceleration is minus a omega square. Okay.
But sorry, in both ends is acceleration maximum.
Yeah. I mean, in magnitude terms, yes. If you're talking about magnitudes, yes. Got it?
Yeah.
Yeah, perfect. Any question?
this point, we're done with today's class. Probably we'll have to take a buffer class. Oscillation is a long chapter, especially because I've made it long. But anyways, still, we're done with important bits. Next onwards, it's going to be a bit easier. These graphs you will have to understand. If you want to just look at it, take a screenshot, try and understand on your own. Okay, you can try. There won't be a class on this Thursday, directly Saturday and Sunday. I'm on vacation right now, so I'm a bit busy. Go back. Uh, as usual, you'll have your Saturday, Sunday classes. Later on, second or third week, you'll have a class on Thursday. I'll let you guys know. Right now, Saturday, Sunday classes. So next class is on Saturday, not Thursday, Saturday. Same time. Any question? I'm going to end the class. Any question? Last thing? Nope. All good?
Yeah.
Perfect. Okay then. Bye-bye, everyone.
All right, thank you, sir.
You're most welcome. You're most welcome. Bye, everyone. Best of luck.